Hello guys, welcome to this course for work, energy and power. A course that I promise that after watching this, you won't get anything wrong in work, energy and power when it comes to the fundamental calculations. So please note that I will not be teaching you definitions, what is work. I won't be doing that. I want to focus on the misconcept parts. The part that people truly don't understand, it is what I am actually offering. Guys, remember to go and click the link on my bio so that you request that we apply for universities, colleges, and bursaries. And also go and tell your friends about this amazing course of work, energy, and power that you have just enrolled into. And of course, I promise you're going to find this course to be extremely useful to you. Tell your classmate, again, I'm trying to be ambitious. I'm trying to reach 20,000 learners to buy this work, energy, and power course. So it could help a lot if you go and tell your classmate and tell your friends so that we can actually achieve our goal. Otherwise, guys, let's actually get down to business. So there are three things that we'll be focusing on when it comes to work, energy, and power. Number one, it is the work done. It is the work done. Number two, it is the mechanical energy. I don't know what's actually happening with this. Okay. Number two is mechanical energy. And number three, it is the work done by the what is the non consecutive I can't write this, consecutive forces, right? I don't know what's up with this camera. The work done by the non-consecutive forces. But in this video we will be having an introduction. I'm actually looking for my other pen, guys. This is so embarrassing. Let me just pause the video and look for my pen. Guys, I can't find my blue marker, but it's fine. I'll use the red one. So I apologize to people who can't see clearly. I really apologize. So on this video, we will be doing the introduction to work done, right? We will be doing the brief introduction to work done. Well, what is work done? Number one, the work done of a force. Let's say we're having the force F. The work done by the force F is going to be force, distance, and the cos of theta, with F being the force, obviously measured in newtons, and with change in x being the distance, and of course measured in meters, and with the cos of theta being the direction, right? And the work done is actually measured in joules. Joule. Okay, let's actually look at a very simple example, right? I want to show you something. I want you to look into this. We're having 0 degrees, we're having 90 degrees, we're having 180 degrees, and we're having 270 degrees, right? So let's say we are having this block, right? This block has a mass of m, and it is actually undergoing the force applied. That is actually around 30 newtons. Let's just say 50 newtons. And then it is actually undergoing the frictional force. Let's say it is actually 30 newtons, right? So I want you guys to understand something. So if we want to calculate the work done by the force applied, this force, it is going to be force, change in x, the cos of theta. So what is force? Force is going to be 50. So let's say this block moves at distance of 5 meters. So change in x is going to be 5 times the cos. So we actually look on which direction is the force applied acting on. The block is moving on this direction. So the force applied is actually acting on the 0 degree side. So the cos is going to be that of 0 degrees. So the cos of 0 is the same as 1 if you hit it on your calculator. So we're going to have 5 and 50. So what is this answer? So we are obviously going to have 50 times 5. That equals to 250 joules, right? So that is the work done by the force F. Suppose we have, we want to find the work done by frictional force. We're going to say Fk changing x, the cos of theta. So Fk, you don't write minus 30, no. This is where you see where the minus is coming from. Don't write minus 30 here. You write it as a positive 30, and the distance, it's 5 meters. The cos, where is it? If you check, the block is moving in this direction, but the cos is acting on the 180 degree side. So it's going to be the cos of 180 degrees. 180 degrees, the cos of 180 degrees is the same as minus 1 times 5 times 30. So this is the same as 30 times 5 minus 1. It's going to give you a work done by friction or kinetic friction of negative 150 joule. Let's say we want to calculate the work done by the normal force. So we're going to have the normal force changing x, the cos of theta. What is normal force? Normal force is measured as mg, right? Normal force is measured as mg. Normal force equals to mg. So we're going to have the change in x, the cos of theta. What is m is going to be m at this problem. What is g? It's going to be 9.8, right? And then we're going to times this by 5, the cos. What is the direction of the normal force? The normal force is always acting upwards. So it means this is going to be the cos of 90 degrees. So we're going to have the cos of 90 degrees. So 90 degrees is the same as 0. 90 degrees is the same as 0. And we're going to times this by 5. And we're going to times this by m times 9.8. So anything multiplied by 0, we get 0 joules. So this is the reason why we always, in a way, ignore work done by normal force. Let's say we want to calculate the work done by gravity. We're going to have gravity changing x, the cos of theta. So gravity is also the same as mass times g, that is 9.8. The distance covered is 5, and the cos, it's actually on the direction of 270 degrees. So we are going to have 270 degrees. This is the same as 0, and we're going to have 5, and we're going to have m 9.8. So this is also 0 joules. So that is why also on Newton laws of motion, we always try to ignore that. So I want to introduce you to a wonderful formula. It is called the work net. The formula work net is said to equals to the change in kinetic energy. So the work net equals to 1 over 2m v final squared minus the v initial squared. But what does the work net equal to? So the work net equals to the work done by force applied plus the work done by friction plus let me just say Fk plus the work done by normal force plus the work done by gravity and all the forces that are actually present within the problem. So let's say we are having a problem like this. We're having a block of 3 kg that is actually moving on a force applied of 10 newtons and a frictional force of 3 newtons. The block covers a distance of 10 meters. Okay, let's say we don't know the frictional force, by the way. So on point A, the velocity of the ball, of the block, is 10 meters per second. And at point B, the block suddenly stops. And they say calculate the work done by the frictional force. Calculate the work done by the frictional force. So what you can do, you can say that, okay, work net equals to 1 over 2m v final squared minus v initial squared. What are the forces that are present? If I draw a free body diagram, I have force applied, I've got my friction, I've got my Fg, and I've got my normal force. So the work done by force applied is present. Okay, it's blurring, I'm sorry. And we also got the work done by friction equals to 1 over 2m v final squared v initial squared. Why did I exclude the work done by gravity and the work done by normal force? Because we know that the work done by normal force and the work done by gravity always equals to 0 joules. So we can actually try to ignore it. So the work done by force applied is going to be force changing x, the cos of theta, plus the work done by frictional force is going to be frictional force changing x, the cos of theta. This would equal to 1 over 2 mass v final squared v initial squared. What is the work done by force? The work done by force applied is going to be 10 newtons. So I'm gonna have 10 times the work done by, this is the distance covered is 10 meters. I'm gonna have 10, and the cos is going to be the cos of 0 degrees, right? Because it's actually moving on the positive side. It's going to be 0 degrees plus. Frictional force, it is what I am looking for. So we want to find the work done by frictional force. So you don't have to expand it. You can just say the work done by frictional force is what we're looking for. This equals to 1 over 2. The mass is 3. V final is 0 squared at point B. And V initial is 10 squared at point A. So this is the same as 1. And this is the same as 10 times 10. That is going to give me 100. Plus work done by force applied. You're going to hit this inside your calculator. You're going to have a half. 3, 0 squared minus 10 squared. This is going to give you minus 150. So it means that the work done by friction, when you take the 100 into the other side, it's going to be minus 250 joules. So that's how you actually use the formula of work done. So on the next videos, we will be diving deep, within the fundamental basics of the work done. Otherwise, guys, enjoy the rest of your day.